All right, welcome to the Explainer. Today we're going to tackle one of the slickest algorithms out there for network optimization, Kruskal's. It's a fantastic example of a greedy approach, and you'll see just how powerful its simple logic really is. So let's kick things off with a classic puzzle. Picture this. You've got a bunch of dots on a map, and your job is to connect every single one of them. The catch, you have to use the absolute minimum amount of wire, with no wasted connections and definitely no redundant loops. How do you do it? Well, that's exactly the problem Kruskal's algorithm was born to solve. To really get a feel for this, let's ditch the abstract points and talk about something more fun. Imagine you're in charge of connecting a group of islands. The possible connections are bridges, and every single bridge has a price tag, a cost to build it. Your mission, should you choose to accept it, is to link up all the islands so everyone can travel between them, but do it for the lowest possible total cost.
Okay, so this perfectly efficient network we're aiming for, it actually has a proper name in graph theory, and understanding it is the key to the whole thing.
It's called a minimum spanning tree, or MST for short. Let's break that down real quick. Spanning just means it reaches every single island. No one gets left out. Tree is a technical term. That means there are no loops, no cycles. You can't start on one island, cross a few bridges, and end up back where you started without retracing your steps. And minimum, well, that's the best part. The total cost of all the bridges you build is the lowest it can possibly be. It's the definition of efficiency. So the big question is, how do we actually find this thing? You might be thinking it's got to be some super complicated process, looking 10 steps ahead, but nope. Kruskal's algorithm uses an approach that's so simple it's almost deceptive. It's called a greedy strategy. The strategy is beautifully simple. Seriously. First, you just make a list of every single possible bridge you could build, and you sort that list from the cheapest to the most expensive. Then you just start at the top of the list, and for each bridge you ask one simple question. Does this bridge connect two islands that aren't already connected? If the answer is yes, great, you build it. If they're already part of the same landmass, you skip it, because building it would create a wasteful loop. And that's it. You just keep doing that until every island is connected. All right, but wait a second. That third step, check if it connects two previously unconnected islands. That's where the real magic and the real challenge is. How do you know that? Especially when your network is getting huge. Checking the whole map every time would take forever. We need a shortcut. Yeah, this is the million-dollar question, right? As we're building out our network of bridges, we need a super fast way to tell if Island A and Island B are already connected, even if it's through a really long, roundabout path. Answering that question quickly is what makes this whole algorithm practical. And the solution is this really clever tool called a disjoint set union, or DSU. The best way to think of it is like a magical self-updating map. It's a special data structure that keeps track of which islands belong to which group, or set. At the very beginning, every single island is its own little group of one. This magic map does two things, and it does them incredibly fast. The find operation is basically us asking the map, hey, what landmass does this island belong to? And it gives us an answer almost instantly. The union operation is what we do when we decide to build a bridge. It tells the map, okay, these two separate landmasses are now connected, merge them into one big group. Thanks to some smart optimizations, these two operations are so fast they make the whole loop checking problem disappear. Okay, so we've got the how, we sort the bridges, and we use this cool DSU map to avoid loops. But why does this actually work? Why is being greedy, always picking the cheapest option right in front of you, guaranteed to give us the best final answer? Why doesn't it corner us into a bad choice later on? Well, the reason we know it works comes down to a really elegant mathematical idea called the cut property. The easiest way to think about it is this. Imagine you draw a line on your map that separates the islands into two groups, any two groups at all. That's a cut. The cut property proves that the single cheapest bridge that crosses that line must be part of the final minimum spanning tree. And since Kruskal's algorithm is always looking at the cheapest bridges first, it's naturally following this rule with every single choice it makes. It's mathematically guaranteed to get it right.
So, how fast is this whole thing? In the world of algorithms, we talk about its time complexity, which is O of E log E. Now, don't let the notation scare you. All it really means is that the algorithm's total runtime is pretty much dictated by that very first step, sorting the list of all the bridges, or edges. E is just the number of edges. The rest of the process, thanks to our DSU, is so blazingly fast that the sorting part is the only thing that really takes time.
And what's really cool is how tough this algorithm is. It has some awesome superpowers. For instance, what if your islands are actually two separate archipelagos that can't be connected? Kruskal doesn't care. It just builds the best network for each one, giving you what's called a minimum spanning forest. It even works if bridge costs are negative, like you get paid to build them. It automatically ignores silly things like a bridge from an island to itself, and if you have two bridges between the same two islands, its sorting step ensures it always considers the cheaper one first.
But Kruskal's isn't the only game in town for finding MSTs. So how does it stack up against its main rival, an algorithm called prims?
And really, when you look at them side by side, the choice often boils down to one thing. How dense is your graph? Kruskal looks at all the bridges globally, which makes it great for sparse graphs, where there aren't that many possible connections. Prims, on the other hand, starts at one point and grows outward, like a crystal. This can be more efficient on dense graphs, where there are connections between almost everything, and sorting them all first, like Kruskal's does, would be a huge task.
Now, this is super important because this isn't just some abstract puzzle for a computer science class. This exact logic is behind how we design real-world networks to be efficient. Think about power grids, internet backbones, or computer chip layouts. It's also used in data science for clustering, helping to find natural groupings in complex data sets. It's a true building block of modern computing.
Okay, so to wrap things up, let me leave you with a final little brain teaser. We know Kruskal's algorithm is guaranteed to find a minimum spanning tree. But what if a bunch of different bridges all have the exact same price? The algorithm will just pick one based on its sorted order, but what if it had picked another one of the same cost? You could end up with a totally different-looking network that costs the exact same amount. It's a great reminder that sometimes in optimization, there isn't just one single perfect solution, but maybe a whole family of them.